quickly? Here we go. As quickly as possible. Basically what we're going to talk about now is the shape of the molecules, okay? So you guys need to have your notes out for this part. We're actually filling in some notes. It's going to be short, okay? But there is a little bit here. So on the molecular geometry, what I'm talking about is what is the shape of the molecules, all right? We haven't talked about that yet. All we've talked about so far is sort of like which one goes in the middle, how many electrons are around it, do we have double bonds or single bonds or that sort of thing. Now what we're going to talk about is how does the shape of the molecule actually work, okay? And why does it take the shape that it takes? So that's, when we're talking about molecular geometry, that's what we're talking about. And with molecular geometry, you need to remember the word Vesper, not Vesper. Okay, everyone tries to call this Vesper, but this is not Vesper, right? It's Vesper, and it stands for valence shell electron pair repulsion theory. See why we call it Vesper? So that you don't have to say valence shell electron pair repulsion theory all the time, right? Because that's too much. All right, so let's look at the name of this theory and see if we can figure out what this actually means, okay? So valence shell, what are we talking about there? What's valence mean? It's the outer electrons, right? Okay. Valence shell electron pair repulsion. What do you think that means, electron pair repulsion? They don't like each other, right? The electron pairs are trying to get as far away from each other as possible. So the theory basically just says, because these electrons are all negatively charged, the pairs are trying to get as far away from each other as they can. Now, why can they stay in pairs? Why is that okay? Do you remember? Why is it okay for the electrons to pair up if they're negatively charged? What can they do so they can hang out in the same hotel room? Well, no, they're both negatively charged, right? You guys remember when we tried to do this with our hands? Yeah, they spin in opposite directions, remember? Am I doing it? Okay, don't try again. I mean, that'll get you distracted for a good 5 minutes. But they spin in opposite directions, okay? That's the up arrow and the down arrow. That's why they can pair up, because they have opposite spins. But once you get two in a room, that's enough, okay? Now, granted, you can actually have a double bond or a triple bond, but you need more orbitals to make that happen. So there are never more than two in the same room, okay? So these electron pairs don't like each other. That means they're going to get as far away from each other as they possibly can. All right? That's the idea here. And the molecule is going to adopt the shape that minimizes those repulsions. In other words, gets those things as far away from each other as possible. All right? We want to move the electron pairs as far away from each other as possible. All right. Is this on your sheet? The common geometries? Okay. So just to look at this, and we're going to actually build these in a minute, okay? So you can have a linear shape. That's when you just have two atoms in a line. Two atoms in a line, okay? That's linear. Pretty easy. Trigonal planar, that's when you have three atoms attached to the central atom. Tetrahedral, that's when you have four atoms attached to the central atom. Now, we're going to go over a couple others that are... Uh-oh. They just lock up. Does that mean everything locked up? Are you still hearing my voice on the video? That's the question right now. Uh-oh. Okay, I think we're all right. Let me see if there's anything else we need to talk about here. Okay. So let me just... Do you have this on your notes? Yeah. Okay. This is kind of a procedure here, and then we're going to go through a bunch of these in practice, and we're actually going to build some molecules that have these shapes, all right? But the first thing you're always going to do is use the Lewis structure, Okay, so you're going to have to make a Lewis structure first if one is not given to you. It's the first thing you always have to do. Then you're going to figure out the bond angles based on the electron arrangement. Okay, you're going to look at the central atom for all your data. In other words, you're going to look at the number of electrons around the central atom, the number of electron pairs. That's what determines all of this geometry. Okay? And then you need to think regions of electron density. So this is something else you have to remember here, rather than bonds. Okay? A double bond has to stay together. So remember, with the example we were just doing, if I have something like this, okay, around the central atom, I really only have 2 regions of electron density because these double bonds can't come apart from one another. So even though there's 4 electrons here and 4 electrons here, we're just going to say that there's two regions around this carbon that we have to worry about. Okay, this is all going to make more sense once we start actually practicing this. All right. Then you need to determine the number of bonding and non-bonding pairs, and that's going to help you determine the shape. Okay. A lot of that probably isn't going to make a lot of sense yet, because we need to actually do some of these first. And let's see. This is the only chart that you have, right? You have this one. It only goes up to 4. We're actually going to go up to 6 pairs around the central atom, because remember, some central atoms can have up to 12 around them, right? So we're going to talk about those as well. All right? So that's basically all we can really do from the notes. The rest of this is going to be this activity that we do. So let me turn this off, and then I'll tell you what to do for the activity. Very short notes that there might not have even been any point to that, but oh well.